Hi all, and thanks for joining this webinar. My name is Christoph, and today we are going to talk about hardware-in-the-loop testing solutions for battery management systems. I am thrilled to have Danielle and Yatin joining this session. Danielle is product expert for SimScape Battery at MathWorks and will show us the latest and greatest for battery modeling and battery controller design. Yatin is application engineer at Speedgoat and will show us a hands-on end-to-end hardware-in-the-loop demo. So let's get started right away. Batteries are crucial for the decarbonization of transport and electric power supply. Embedded controllers need to be developed and tested that control electric powertrains and their components, such as systems for managing and controlling batteries. Battery systems are evolving. Manufacturers aim to use new battery chemistries that are more energy dense, perform better, or are just more cost effective. Battery packs must provide more capacity while using less space and remaining safe. There's also a trend to increase battery voltage levels above 800 volts to decrease conduction losses. Some standards already consider charging voltages of up to 1500 volts. Battery systems need battery controllers, typically referred to as battery management systems or BMS, and testing those BMS controllers needs to be fast and safe and should ideally be done without requiring the battery hardware. BMS are essential for the safe operation of the battery. BMS maintain the battery performance and optimize the battery life. Battery management systems typically monitor the cell voltages and temperatures at different locations. BMS measure the pack voltage and its charge or discharge current. They estimate the state of charge of both cells and of the pack. BMS also controls cell balancing. So, for example, if a cell parallel assembly has a higher state of charge, it gets discharged by a balancing circuit in the BMS. BMS control the connection to external units for charging and discharging. And last, but certainly not least, BMS protect the system from faults like overcurrents, overheating, or short circuits. Testing battery management systems using real batteries can be cumbersome, because battery cells behave differently over time and also based on their different charge or discharge cycles. Therefore, it is difficult to reproduce testing of the BMS core algorithms such as cell balancing and state estimation. Testing extreme conditions of high voltage systems like overcurrent or high temperatures can be dangerous with genuine batteries. Batteries, BMS systems and their algorithms evolve and require testing many parameters, configurations with many different types of battery packs. So while testing with real batteries can be dangerous, time-consuming and expensive as we've just seen, it is possible to test BMS using a digital battery twin called hardware-in-the-loop testing. Emulated battery cells and packs provide real voltages and power, controlled by models. Those models can easily be adapted to match different battery cells or pack architectures, including the thermal behavior of the battery. Test automation and support for continuous integration enables you to test requirements-based and 24/7. You get steady returns on your investment as you can adapt your test infrastructure to advancing technology. So I hope these advantages convince you to conduct hardware-in-the-loop testing of your battery system using model-based and emulated batteries. For large battery packs, the BMS has mainly three separate components. The battery management unit is like a central unit including algorithms like state estimation. It also communicates with other control units in the vehicle and executes high-level protection algorithms. The cell monitoring unit, or CMU, measures the temperature and voltage of each cell. It also includes an electric circuit for cell balancing. As the CMU needs to be close to the battery cells, it is typically composed of many separate units connected via an isolated daisy chain protocol. Finally, the power distribution unit measures the overall battery pack voltage and current. It also controls the electrical connection to external units and implements the electrical protection of the pack. You rarely need to test only the battery management system. So you can leverage Speedgoat test systems to integrate digital twins for connected components such as chargers, motor drives, and even complete powertrains. For example, you can also test the BMS together with a real electric vehicle charger by using a bidirectional power supply or charging protocols like CCS. You could also test your BMS together with a motor drive or even the full powertrain. For this case, you would need bidirectional power supplies or power amplifiers. industry-specific communication protocols, and an electric motor emulator to thoroughly test the motor drive. So on a high level, the BMS Hill testing solution by MathWorks and Speedgoat that I've just presented is designed to assist you from the early development stages up until commissioning and certification. So you benefit from a fully Simulink integrated solution that provides flexible and automated workflows, powerful digital twin simulation software and hardware emulation solutions, and modular hardware-in-the-loop racks that can scale with your need. Before we dive deeper into these solutions, let's review today's webinar agenda. First, I'll introduce our solution's key capabilities and workflows. We will then shift the focus on key aspects of BMS Hill testing, starting with a hardware demo presented by Yatin, and then Danielle will demonstrate battery modeling and the design of BMS algorithms. So let's get started. The workflow for testing your BMS with a Speedgoat battery cell emulator, or BCE in short, typically consists of modeling the battery cells first and other system-level models using Simulink and Simscape Electrical, and then deploying it to a Speedgoat test system. The Speedgoat test system will typically have a real-time system, battery cell emulators, and a safety compartment to place your BMS. The cell monitoring units can be connected at 400 volts or even more. Once deployed, the battery cell emulators will have the thermal and electrical behavior described from the models and are connected to the BMS. The development computer serves as a user interface like for tuning and signal monitoring. And once ready, you can perform automated testing for multiple configuration, multiple testing scenario, or various battery models. Testing of a BMS is scalable and can go from a desktop configuration with 12 cells to rack configurations with 252 cells in series and voltages up to 1.3 kilovolt. For example, typical voltage levels for electric vehicles are 400 or 800 volts. Speedgoat BMS test systems can include temperature sensor emulation, electric power emulation, and isolated I/O and communication protocols. A Speedgoat BMS test system has 5 key capabilities. First, you can scale your test system as we've just seen. Second, you can connect your devices to the real-time target machine using your preferred I/O and communication protocols. The test system is designed for use with Simulink and will run the individual battery cell plant models, thermal models, cooling dynamics, and other system-level dynamics. Then we have the battery cell emulator that handles the electrical emulation of each battery cell. We can have up to 252 cells connected in series, leading to a system voltage of 1.3 kilovolt. As it's essential to consider thermal effects, we offer a temperature sensor emulator capable of emulating various sensors like PTC or NTC. Finally, the fault insertion unit will test our BMS for short circuits, reverse polarity, and various broken wire situations. A fourth key capability is the possibility to thoroughly test just parts or the complete power distribution unit. Testing the PDU may require emulating high voltage sensors, shunt sensors, current sensors, as well as pyro fuses, isolation testing, and many more. Finally, the BMS test system leverages Simulink and other MathWorks products for modeling, instrumenting, and continuous integration. You start by creating a digital twin of your battery using Simulink or Simscape. To build your model, you can drag and drop cell library components or use the Battery Pack Builder app, which automates the building process for a desired pack topology. We'll hear more from Danielle in a bit. You can also model cooling systems and simulate thermal effects like insulation and heat exchange, and create a system-level digital twin that includes a power converter and motor drive. Finally, you can add the necessary hardware emulation and interfaces to the BMS. The battery digital twin model runs on a Speedgoat hardware-in-the-loop simulator, such as the Performance real-time target machine. You can also use this as desktop Hill test bench for simple testing scenarios, such as BMS controller logic testing. To test a BMS with cell emulation and real power interfaces, you'll need a rack setup, configured to meet your simulation and controller interface needs. In addition to the hill simulator, a typical BMS hill rig includes those components. A stackable cell emulation unit, or several of them, allowing you to simulate full battery packs with cell-level fidelity. Additional modules allow you to emulate temperature sensors or insert electrical faults if needed. Then a safety compartment for your BMS controller, as well as power supplies that can emulate the high voltage and low voltage battery packs and additional current and voltage probes. I/O solutions allow emulation of the various buses and isolated protocols, the cell monitoring units, as well as the current shunt sensor and other components. This ensures that the battery's digital twin appears to the BMS controller precisely like the actual battery, from signal to bus and power level communication. Ultimately, you can test all BMS components, such as individual cell monitoring units, the battery management controller, or the entire BMS system with or without the high power interfaces. Finally, you can set up the whole system for interactive testing, for instance using Simulink and MATLAB apps, and further streamline the setup for requirements-based testing using test automation and continuous integration workflows. Let's move on to focus on a BMS Hill testing hardware demo. Yatin, the stage is yours.
Thank you, Christoph. I will be showcasing a BMS Hill test setup in action. It is used to test the BMS algorithm with the battery pack being emulated in Speedcode battery cell emulator and test faults in the system. BMS testing ensures the safety and reliability of battery systems. Hill simulations allow engineers to access the battery management system's response to varying battery conditions, optimizing performance, and extending battery life. It also shortens validation times and increases the range of test scenarios. We are using a smaller scale demo test setup. The BMS is composed of a battery management controller unit, a single cell monitoring unit, and interface through NXP's isolated protocol. The Hill test system is composed of a performance real-time target machine equipped with a CAN IO module and a battery cell emulator emulating 12 cells of a 48-volt battery. In the bottom of the cabinet, we have integrated an interface panel showing analog measurements of cell level and an interface connector to the BMS controller. Since our BMS setup does not include a junction box, the current and the voltage of the battery pack are relayed to the BME through a CAN bus. I will now move to the Simulink environment and explain how a battery cell emulator can be integrated into a bigger system, which consists of a battery management system and a 48-volt battery which is emulated in the battery cell emulator, and show how different test scenarios can be implemented to test the BMS. This model consists of three main components: a BMS control algorithm running on NXP battery management unit, a battery, and a user interface for efficient testing and monitoring. The model runs on real-time target machine and the cell's behavior is emulated by the battery cell emulator. Let's explore the battery model. The battery model consists of a battery module, a passive balancing interface, and a fault insertion subsystem. The battery module is made of 12 cells of 4 volt each, connected in series. The battery is modeled with SimScape battery using the battery builder app. The passive balancing interface inputs the balancing currents from the battery cell emulator and balances each cell, giving out the effective voltage. Short circuits are also implemented here. The battery builder app will be presented by Daniel later in the webinar. Let us now see how Speedcode battery cell emulator can be integrated to this model with the interface blocks. These blocks allow us to set up BC and convert cell voltage signals into electrical isolated signals. These signals are ones being emulated by the battery cell emulator. Speedcode provides a simple tool to set up a battery cell emulator, a fault insertion unit, or a temperature sensor emulator. One can easily add the required devices and select the number of devices connected to their setup. The user can also update their device firmware using the Utilities tab. Let us now see how a battery management system is interfaced using this model. It includes a CAN interface that transfers battery data, including the cell temperatures and pack currents. At the same time, it receives CAN signals from the BMS controller, such as the state of charge, current limit for charge and discharge, and fault diagnosis data. Using the seamless integration, you can deploy your model onto a hill simulator and run it with a click of a button, all from Simulink. Let us run a hill simulation and observe signals from the battery cell emulator. Using this custom user interface, one can easily inspect the state of charge, temperature, voltage, and currents of each cell, as well as the balancing currents that flow from the cells to the cell monitoring unit. Additional gauges allow monitoring of SOC, charge and discharge current, as well as fault diagnosis. To start the demo, we use Simulink instrument panel to override all cell voltages to 4 volts. We can connect a digital multimeter and confirm that the battery cell emulator correctly drives the requested voltages. We connect the terminals of the first and the 12th cell and see that the cells are connected in series, resulting in an overall voltage of 48 volts. Now let's validate the BMS cell balancing. To do that, we recreate a charging scenario by switching the BMS from standby to charging mode with a charge current of 5 ampere. We see that the module SOC and the SOC of various battery cells increase accordingly. By inspecting the BMS data, we see that the current charge imbalance across 12 cells is about 75 millivolts. The BMS is configured to start balancing if the imbalance crosses 100 millivolts. Let's trigger the balance of cell 8 by changing its voltage to 4.1 volt. Cell 8 is in balancing mode with a discharge current of about 110 milliampere. Let's switch to driving mode, and as expected, the BMS controller stops cell balancing. We also see the SOC and voltage decrease and the discharge currents being calculated by the BMS. Let's discharge the battery with 20 ampere. The BMS allows discharge limit of minus 90 ampere for the present battery state. So if we override this value by minus 120 ampere, the BMS immediately triggers an overcurrent fault. The configuration panel lets us insert faults very easily. We can add short circuit or over voltage or temperature faults. These are the faults that we implement in the model, but you could equally have these implemented at the signal level using Speedcode fault insertion unit. Now let's talk about how tests can be automated using Simulink Test Manager, and requirements can be linked to a test scenario. All the predefined tests are designed for the system model that I just showcased in the previous section. This is the requirements editor, where requirements for system can be imported using an Excel or a Word file. This is an example of some requirements of a BMS system. As you can see, it clearly shows what requirements are implemented, tested, and verified. It also shows if a test has failed to fulfill the requirements. Each requirement is linked to a test or a subsystem where it's implemented. Let us run some predefined hill tests using the test manager and see how they work. This is a requirement-based hill test that overrides all cell voltages to 2 volts. After running the test, we can compare the test data with our expected results and find faults in our system. Each signal and parameter can be compared using the Simulink Test Manager. We can check the requirements editor after running a test and confirm that all the tests linked to the requirements are verified. You can observe that the color has changed to green, which indicates that the tests have been verified. We can also run an automated script for continuous integration testing for hill test that runs all the defined tests from Simulink Test Manager and generates a test report. Now let's talk about MATLAB App Designer and MATLAB Apps. MATLAB Apps open access to real-time application for non-Simulink users and enables efficient testing with custom apps designed in MATLAB App Designer. Here's an example for a custom app that has been designed to test a BMS controller. It includes all the basic components needed to run an application on a real-time target machine, as well as the necessary battery data that can be manipulated and observed within the app. It is similar to the UI shown previously on Simulink. The code to program this app is also available. You can run the app from the App Designer and test its features. As mentioned before, it lets the users connect to a real-time target machine. The user can choose from model in the loop or hardware in the loop mode, run the application on the host PC or a real-time target machine. As shown in the previous demo, all the test scenarios can also be tested using this app, like changing the battery charge and discharge current, choosing test scenarios, and adding faults to the system. You can also use a MATLAB app to run tests as a standalone app, which does not require Simulink to run. Now you must be wondering where to find this reference example, as it can be a starting point for your upcoming project. You can go to speedcode.com and click on Knowledge Center, then select reference examples, and you will find all our reference examples here. After logging in, you can also download the model here. Thank you for your attention. I will pass the control to Daniel now.
Thank you, Jiating. Now I'm going to talk about battery modeling and BMS algorithm design with the SimScape battery. For control development, the journey typically starts by defining requirements and simulating both plant and controller in a desktop environment. The BMS algorithm development workflow has 4 steps. Step 1 is to define control requirements. What are the functions will be included in BMS? It may include cell balancing, state of charge, and state of health estimation, the charging and discharging current limits calculation, fault management, constant current and constant voltage charging, and so on. Step 2 is to create a battery pack model with the SimScape battery. Step 3 is to develop BMS algorithm with the Simulink and SimScape battery. And the last step is to evaluate the BMS algorithm in closed-loop desktop system simulation. This slide is an overview of the value and capabilities of SimScape battery. SimScape battery provides design tools to design and simulate battery and energy storage systems, including electrothermal cell behavior using equivalent circuit model, electrochemical cell behavior using single-particle battery model, which was released in 24A. We had tested 12 single-particle battery models connected in series running successfully on SpeedCode hardware in the loop. Battery pack design with Battery Builder app or MATLAB API. Adding non-intrusive battery faults like internal short circuit, disconnected cell to simulate a loose wire bond, and exothermic reactions to simulate thermal runaway events. And pre-built battery management system library blocks. With the SimScape battery, you can evaluate the battery pack architectures for electro and thermal requirements, verify robustness of discharge, charge, and thermal management algorithm, and validate the algorithm using model-in-the-loop desktop simulation and hardware-in-the-loop testing. SimScape battery models integrate directly with block diagrams in Simulink, state machines in Stateflow, and MATLAB functions, so you can simulate your entire system in a single environment. With the SimScape battery, you can design your battery pack with Battery Pack Builder. You can choose the app or MATLAB API to build the battery pack from single cell level, parallel assembly, module assembly, and battery pack level. You can visualize the pack geometry and topology at each stage of the design, and define and visualize the simulation strategy. SimScape battery allows you to customize your model fidelity based on your simulation needs. The detail option provides the highest fidelity. The battery object uses one electron model and one thermal model for each battery cell. The lambda options provides the lowest fidelity. The battery object uses only one electron model and one thermal model. You choose the lambda options when you want to have the fastest simulation. You can choose grouped to further customize your model fidelity. For example, certain cells in a battery module have the same electrical and thermal behaviors and are different from the rest of the cells. By selecting the groups of cells to have identical thermal and electrical conditions, you can reduce computation and accelerate the simulation. For example, there are 36 totals. Instead of simulating every cell in detail, you can customize your simulation strategy. The left figure shows the battery model is customized to 13 unique conditions. Each unique condition means a different electrical and thermal condition. The right figure demonstrates 25 unique conditions. In this video, we show how to use the Battery Builder app to create a battery module from a cell model and generate library blocks that we can use like other SimScape library blocks. When you load the Battery Builder app, it already has examples of cells, parallel assemblies, module assembly, and pack. You can create your own cell model and define its properties, including geometry, mass, weight, energy, and model options, and so on. We use the battery equivalent circuit block, which allows us to add non-intrusive force later on in simulation. We then create a parallel assembly using the cell we just created. We can define the number of the cells which is electrically connected in parallel. In this case, we have one cell per parallel assembly. Then we created a battery module. We define the number of parallel assemblies as 12. We chose the balancing strategy as external, and the battery chart we can visualize the model resolution. We use the model resolution as detailed. Once we have defined our battery design, we can create a SimScape library block of the battery module to use in simulation, and define the parameters in the generated M script. Now we have demonstrated how to build a battery model using the Battery Builder app in SimScape Battery. Let's look into the battery management algorithm that the SimScape Battery provides. This slide is an overview of the battery management algorithm, including charging and discharging, constant current, constant voltage, passive cell balancing, state of charge, state of health, state of energy estimation, and battery capacity estimation, protection, fault management, and thermal management. For passive cell balancing, parallel assemblies is defined as cells connecting in parallel. The cells within a parallel assembly will naturally balance. For each series connected parallel assembly, there is one cell balancing circuit. This is a demonstration of passive cell balancing shipping example. As you can see, the parallel assemblies start with a different SOC and eventually balanced over time. The example here demonstrates the SOC estimation using common filter. The solid line is real SOC and the dotted line is estimated SOC. Even though the initial SOC estimation are off the real SOC, but the SOC estimator does a great job of estimation. We talked about cell balancing and SOC estimation. Let's move on to thermal management. SimScape Battery has 3 different types of cooling plates available: edge cooling, U-shaped cooling, and parallel cooling. Similar to battery pack itself, you can change the simulation strategy of cooling plates to meet your model resolution needs. The top one is just a lambda model of a cooling plate, one single model. The bottom one is 8 elements to model the cooling plates. For initial design, it's useful to just use a lambda model to get initial parameterization. But if you want to see the temperature gradients, you need to have a higher resolution. In the example, the battery model is a module with 12 pouch cells coupled with the cooling plates with 2 channels. The cooling plate is discretized along the x and y direction. The SOC estimation of the module is estimated with a common filter. The estimated SOC and parallel assembly voltage are used to tune a constant current, constant voltage profile. The module is actively cooled by battery coolant control. Let's look at the simulation results, specifically the temperature of the module and the cooling plate. The cooling plate and the battery module both start at 25 degrees C. When we charge the battery, we see both battery and cooling plate's temperature increase. Then we turn on the coolant flow, and the temperature decrease. The SOC estimation is also very accurate, as the left figure shows. In this section, we showed the value and some capabilities of using SIMScape battery during BMS development workflow. There are 4 takeaways: battery pack builder, no matter app-based or MATLAB API-based, scales a cell up to a battery pack level. SIMScape battery comes with a wide range of pre-built BMS algorithm, and you can customize your modeling fidelity of battery pack and cooling plates. SIMScape battery supports non-intrusive fault injection and code generation. Now I'm handing it over to Christopher to conclude.
Thank you, Danielle. We can now conclude our webinar. Let's move to the key takeaways. There's a single key takeaway for you today. Speedgoat Test Systems and Simulink provide you with a testing solution for all aspects of BMS testing. Why is that? Well, first, you can emulate all relevant components, including battery cells, for testing and validating high voltage BMS hardware, including electrical flow for cell balancing, temperature emulation, and faults. Second, you can use MathWorks products like SIMScape Battery to design algorithms for battery management systems and test them against various battery pack models, including thermal and electrical dynamics. Finally, you can integrate the solution into your existing testing framework. You can automate testing and test requirements-based. Thank you for staying with us until the end of this webinar. You want to learn more about real-time controls testing? Then find additional content linked here.